Welcome again. And last lecture we talked about some properties of perspective projection. So I'm going to continue with this theme today and try to derive a few more interesting properties. So last time we studied that parallel lines converge to a vanishing point. Today we are going to take up the next property that I listed then, which is that nearer objects are lower in the image, as you see here by considering the poles and the bottoms of these poles in this diagram. How do we go about proving this? That's the question. So let's start by noting that all of these objects are on a ground plane. So on the ground plane, the following is true. The y coordinate in the world satisfies the condition that y is equal to minus h. So think of h as the height of the camera or the person taking the picture. So if the equation of the ground plane is y equals minus h, then any point in the ground plane is going to have a project to a y coordinate which is y equals minus fh over z. So that's just from the equation of perspective projection. So can we derive anything further? So let's just follow this through. So suppose we consider z going to infinity. So we are considering faraway points. What will happen to little y? So little y will go to 0. So, okay. And now we can consider points which are closer to us. So if there are points which are nearer to us, what will happen? We'll have y will be more negative. So what does that mean? That means that it will be lower in the image. So if we consider the points here, these and so forth, so we have points associated with depths z1, z2, z3, and obviously z3 is greater than z2, which is greater than z1. And the associated y coordinates, they're all negative, and the y coordinate for the point 1 is the most negative, intermediate, and least negative. So in other words, we see that nearer points are going to be lower in the image plane. Okay, here is another obvious kind of statement, but we want to prove it using our techniques, that nearer objects look bigger. So what I'm going to do is I'm going to take up one of these poles, and I'm going to derive what its length is in the image. So its length in the world is going to be L. So that's the height of the object out in the world. In the image, we are going to consider the point corresponding to its bottom, and its bottom is at x, comma, minus h, comma, z. So where does the minus h arise from? This is the height of the camera. Okay, so what's the top of the point going to be? So let's consider this location. So it's the same x coordinate, the same z coordinate, but the y coordinate is different and it's larger by L. So L is the height. L is the height of the object. So this height is L. So that gives us the following equation for the top of the object. And now things are pretty straightforward. We just have to derive what the bottom projects to. So what does the bottom project to? It's going to project to fx upon z, comma, minus fh upon z. And what does the top project to? Fx upon z, f L minus h upon z. So if I consider the difference between these, what is that? That's essentially FL upon Z. And that you can think of as the vertical size of the image in the projection. And clearly we have the property here that large Z means that this is smaller. So in a similar way we can prove various other properties that are true of an image created by perspective projection. So it's all quite straightforward. You just have to apply these rules, fx upon z, fy upon z, and just try to figure out what are the appropriate choices of x, y, and z to plug into these formulas. Let's try to get some more intuition, but before we do that, I want you to have in mind a physical model which avoids inversion. And I have shown that here. So imagine here that there is a person who's standing there looking at some object. This is the object in the world. And what we do is we have a pinhole. So this is going to be the equivalent of the pinhole. But instead of having the image plane which is at F behind the pinhole, we imagine a virtual image plane which is F in front of the pinhole. So it's just, if we are considering the same F, but we are putting it in front rather than in the back as we had earlier, instead of what we had earlier. Okay, what is the advantage of this? So essentially, you can imagine that you have a transparent sheet. So you have a transparent piece of glass which you put at a distance of F in front of the pinhole. So the image is created as follows, and again the similar triangle reasoning will go through, and we will be able to derive the projection equations. Little x equals fx upon z, little y is fy upon z. And now what's cool about this is that we've got rid of the minus signs. So in my last lecture I talked about getting rid of the minus signs in software, or just inverting the image top down and left to right. Here you can think of this as a physical model which you can keep in your head as a way in which perspective projection happens with no sign inversion. So one way to think about it is that this is how an artist should operate. An artist is trying to paint a picture of an external world on an easel. So this is going to be kind of the artist's easel on which he or she is trying to paint this picture of a tree outside. And they want the picture to be such that a person situated at the right location would get exactly the same set of rays from the painting as he or she would get from the real world. And then obviously they would imagine a construction like the one I've shown here. So what this makes very clear is that what's very important is the location of the pinhole, or sometimes we will call this the center of projection, because all the rays which form the image go through the center of projection. And perspective projection is really a mapping from points in three-dimensional space, x, y, z, to this collection of rays. And what's the collection of rays we are talking about? All the rays which go through the center of projection, and I'll abbreviate it sometimes as COP. So this is the fundamental way to think about it. Once you see it this way, you realize that the projection surface that we considered here, it is not very important. I mean, we can put a plane there, we could put a sphere. So you could imagine that you have a transparent globe, and the center of that globe is the pinhole, or whatever smooth surface you like. It doesn't matter. We just need some way of recording the intersection of rays onto a surface. So this shows up sometimes in discussions when people are confused that when in human perception, images are created on the retina, and the retina is not flat and it's not exactly spherical. It doesn't matter. All you need is a way to record in a one-to-one fashion the set of rays going through the pinhole, and each ray corresponding to a set of points out in three-dimensional space. Thinking of it this way also makes some other intuitions more evident. What's the right way to measure image size? So we could think about different ways of doing it. You could measure image size in pixels. You could measure it in microns on the image sensor. But let me argue to you that the right way to measure image size is visual angle. So I've shown that in this diagram. So we have some object out in the world, and it creates a certain image. But what I can do is to measure the length of this image with this visual angle theta. And this is the visual angle subtended at the center of projection. How do we measure this theta? In a standard way, by radians or degrees or whatever. So this is a measure of natural measure of image size. And once you have this measure of image size, you can of course always convert this into size on the image plane, because we are going to have a simple relationship. So theta is equal to some L upon F, where F is the distance between center of projection and the image plane. So, but measuring the size of an object on the image plane in degrees, therefore, is a very natural thing. So we do this all the time when we talk about fields of view of cameras or the field of view of the human visual system. We always describe that in terms of degrees. We don't measure it out in terms of megapixels or number of cones and so on. Degrees is subtended at the center of projection is the natural unit. I'll give you some examples of what one can do once you realize that this is the natural unit. We can calculate for some common objects what size they subtend on the retina. So let's take the example of the human head. So the average human head is 9 inches high. So suppose that you're looking at a person who's 9 feet away. So then what you're going to get is that the angle theta is going to be 1 upon 12, because you have 12 inches in a foot. So this 1 upon 12 is in radians, of course. So that corresponds to 4.8 degrees. So if the person was at 18 feet, what would we get? We would get that the head would subtend 2.4 degrees. So note that this gives you a way of measuring distance, because let's assume that all human heads are roughly the same. So the brain has access to the size subtended on the retina. So if the size is 2.5 degrees, you can say, I'm looking at a person who's 18 feet away. So this is quite convenient. Let me conclude my discussion of perspective by trying to capture the big story, which I think can be summarized in two main principles. First principle is that objects which are far away look smaller. Look smaller meaning that the angle subtended on the image plane is smaller. And the basic fact here is the scaling factor of 1 over z. So when z is larger, you're going to get a smaller projection on the image. So we have studied this in great detail already. The second effect which I want to point out is that of foreshortening. Objects that are slanted with respect to the line of sight project to smaller sizes on the image plane. And the scaling factor here is cosine sigma. So let me define sigma. So sigma here is shown in this figure. So we have the line of sight from the eye, and then we have the surface normal to this surface which I have shown here in blue. And sigma is the angle between the two. So if a surface is directly in front of us, sigma will be 0. If the surface is completely edge on, then sigma will be 90 degrees. So sigma is the angle between the line of sight and the surface normal, and sometimes we call sigma the surface slant. And essentially this is going to cause a further diminution in size by a factor of cosine sigma. We can get into this in more mathematically precise, in a more mathematically precise way later, but I think you can get this notion quite intuitively. So these are the two main effects of perspective projection: a distance effect and a foreshortening effect. This is why if we have a circle in the world, it will typically project to an ellipse, and the ratio of the major to minor axis is going to be related to how the circular disk is arranged with respect to the line of sight. Finally, I want to conclude by talking about an approximation to perspective projection called orthographic projection. And we use this quite a lot. And the reason is that it makes the mathematics much simpler in certain times. When is this approximation valid? This is an approximation to perspective when you're looking at an object which doesn't have that much depth variation inside it and is relatively far away. So imagine that here is the camera indicated by the eye, and you're looking at some object, and this distance might be like 20 feet or something like that. And the depth variation within the object is more like 1 foot. So that's the kind of scenario. You're looking at some smallish object relative to the distance that it is with respect to the camera. So what happens there? Let's derive some equations here. So essentially the perspective effect is going to give me that x equals fx upon z1 and x2 is fx2 upon z2. Okay. Now what we can do is to assume that this f upon z1 and f upon z2 are approximately the same. So if f upon z1 approximately f upon z2, in which case we can then say x1 is some alpha times x1 and x2 is alpha times x2. Okay, so this of course is the so this is image, these are the image quantities. So what we have here is just a scaling, so a scaling of the x coordinates. And what will we do for the y coordinate? It's going to be somewhat similar. y1 is alpha times uppercase y1 and little y2 is alpha times uppercase y2. So when can we make this assumption that f upon z1 is roughly the same as f upon z2? It's when the change in depth inside, so when z1 minus z2 is small relative to z, and that's the setting in which we make orthographic projection. So orthographic projection you just assume that there is a constant factor of shrinkage due to the distance, and the distance is assumed to be approximately the same for the whole object. Okay, thank you.